Rete. It's an algorithm developed in the 80s, actually, and by a guy named Charles Forgy. And so it's nothing new. And when we think of artificial intelligence, we usually think of machine learning, deep learning, because this is quite hyped right now. But there are other types of AI, such as that, which solves different problems with less data. And the problem that Rete is trying to solve is the one in which we find ourselves when we have to compare a lot of business rule against a lot of data. And we have to constantly screen for the applicability of those business rules and maybe make inferences and then assert new data, which will in turn trigger new rules. And we have to do it in the loop all the time. So super interesting paper. I'll publish a presentation later so you can have a look if you want. And Rete is it's a way to create also expert system in this type of artificial intelligence. An expert system has different components. I hope you can see the part on the right because there is the attendance on the right side or me. But basically you have human expert, for instance, a doctor or a veterinarian. Then you have a knowledge engineer that usually helps the doctor transfer their knowledge from their brain and their reasoning and the way they think about problems and solve them and find solution into the algorithm itself. And then that's what I created myself, or I adjusted from the Rete original paper called Retex. And the Retex has different layers, which is the knowledge base, an inference engine, which is the actual algorithm, and an interface with which you communicate with the user. So get input, ask questions, print something, call an API, and do anything you have to do as an assertion. So that's an example of a little part of the knowledge of a veterinarian brain input into the Rete algorithm. In this case, we're seeing like there is a dog node. There's a little graphic there with vomiting in the area, but that's actually the point. Like we want to check some gastrointestinal issue, checking for the breed, whether this is a variable or not. And so we can visualize and debug this kind of data, this kind of information in an easy way. This is done using D3, by the way. A rule engine is nothing but a list of business rules to simplify very, very much. A pattern matcher that is matching constantly rules versus data from the user, and the user input, which we saw already, and is usually represented with a struct or something called working memory element. And the rules are actually checked with the forward chaining algorithm. And as we already know, of course, this is a flavor of the Rete algorithm. The rules, I decided to implement them into the Rete algorithm as just a map of given and then. So either a struct or just a map containing list would work and suffice for the algorithm to work. The assumption to format to code this algorithm into the Elixir language was there were actually two. One was that the word is made of triples, actually quadruples sometimes, and the other one is that we'll see in a second, the word is made of rules. So why triples? Because we tend to simplify the word here with owner, attribute, and value, and the predicate, depending on the fact that we are writing the given of a rule or a then. So when something is true, then something else is true as well. That's an inference in this case. So what we see here is an example of a real rule in Retex, and some structs as attribute and working memory element. We already saw that that's the input from the user or even the inference itself. So what gets input again into the algorithm. And here we see how we split the word into fever is greater than something, or the name is Charlie, has generic weakness, is true or false. And this is something that we can ask the user and try to input into the algorithm with the working memory element. So as we already said, the word is made of rules, which means that the right side infers the left side of a rule. So we have just given and then, and that's how we format them. And this is perfectly valid production, so-called production or rule that we can create and add into the algorithm. So we saw in more detail, we have facts and working memory elements. Those are nothing but structs in the Retex algorithm. And the working memory element is just a struct, so it just gets as an input, so it's the interface pretty much for the user and for the expert. And as attribute, another type of facts that are in a folder facts of the Retex, if you go and check it out, is something that then gets translated to the nodes of the graph. So at a high level, we can say that Retex just a sequence of compilation of the rules, activation of those rules, and the update of the algorithm itself. It's a stateful algorithm. It was quite challenging to implement it in Elixir, but we'll see later what I found out and why it was super nice, actually clean. So here you see on the right side an example of Retex just working, like creating a rule, in adding some input from the user, and then we can check the agenda whether or not there is something new there or not. To simplify the creation and of expert system in Elixir, I've also come up with a very simple, very brutal DSL, which has to be improved, but it's just an initial phase, which is called Sanskrit. This is also open source and it's free there. And you can see on the left side how it's parsing statements. And on the right side, you can see an example of a more high-level interface where the rule is not anymore just a map, but it's rather a struct. And you can just say add rules, and et cetera, et cetera. So how, like for me, it was really tricky to get how the compilation of the Rete algorithm works, but specifically in Elixir, because by itself and with other mutable languages, that's quite straightforward. You just mutate objects and keep the state, and that's it. But with Elixir, you don't want to really change the structs and mutate things in a graph or something. So you want to keep the state somewhere. But as an overview, what I did was get the given of a rule. So here there is some pseudocode that says just the dog name is Boris, the owner age is not 25, and it's a customer. Then just translate those into the so-called alpha network or one input node. And here you see how I would compile them. This, you can do it on a piece of paper, but I'm using the lib graph there and just taking each of those statements one by one. Take dog, create a branch from the root, dog. Then take name Boris, this is a test node in pseudocode, and I will add it there, and I will add all the others in the same way. As you can see, the owner is not duplicated because it's just once, and that's one of the beauty of the Rete algorithm. Another really cool thing about going on that project and on that journey was the use of protocols that I've been able to do. As you saw it already, and I already mentioned, each line of this given statement is a nice attribute that translates into one or more nodes in the network. And in order to do that, I just pattern match the alpha network protocol to the type of node. So if it's a has attribute, it's 3 nodes. If it's an is-a statement, it will be 1 node because it's just a type. Like let's say that we just want to check that the dog exists. And from that, we just pattern match, extract information from it, and create the graph. As you can see here, when we do add vertex, add edge, etc., we're just connecting from type to attribute to test node, etc. And we don't even care about the duplication of nodes, as in other language you would do, because the underlying data structure, which is libgraph, is gonna just do it for us. And then the biggest challenge, I think, was the beta network, how to connect. Like we say that the activation of a rule is the fact that all the elements of a given are known to be true. In order to do that, they all have to be tested, right? And connected somehow. So in this case, we see how we connect each element of the given, so each element of the list in the given or then of the rule, in one another 2 by 2, because that's the way you would do it in Rete. So here, for example, we see the first line, so dog name Boris has to be true, and then if that is true and the dog owner age is not 25, then those two become a node, and this is what you see here. And then those two together become AB, and then they are connected to C, which is another node, and this is what you see here as well. So we can go on forever, and then we will just build the graph. So that was particularly easy when you do pattern matching with just a list of at least 2 elements and then 1 element. So that's how I created the whole beta network. And in Elixir, that was super, super easy. I mean, it took me a while to figure out how to do that, but then that was actually very clean, and in very few lines of code, you got the whole second part of the network of the Rete. And so how, now that we have the network and it's like just this directed acyclic graph, how do we activate things, and how do we get to the discount of the 10% for the user? That's what we do once we compile it. We start asking the user, for instance, what's the name of the dog? And they will say Boris. So we compile that into a struct, which is dog name Boris, and go from the root and then try to branch out to every other underlying node. And then we'll find, for instance, dog, which is matching the first element. This was the original triple. Then the name Boris, that's actually true. So it's red because it's active. Then we go down. That's like a 2-input node. And here we can partially activate such node, such as beta memory, because just one side of it, it's called usually left side, is active. And the algorithm will keep the state like that, just in a map. Because what we do is just a map reduce over the network. All the time we add a new working memory element. That was actually very nice to combine with the lib graph. So we can say out neighbors of the current node, doesn't matter really where we are in the graph. We just say whatever is branching out from you, just test it and reduce it and find activations and store them into a map, which is the end struct rated. Here we see how we use the activation protocol and the pattern matching together. So that's a type of node that will be basically the dog node. And that's, here we see how we are trying to activate it. So in this case, we will actually be active because the node type is a variable. So we'll say, whatever is a variable here always matches, and the identifier is actually that variable. Create the token, create the activation, and pass it down and continue. Then we'll keep going and asking the user, what's your age? 29, okay, good. Let me go check the owner. Yes, that's now active. That's perfectly fine. So it's active, and now we activated finally the full beta memory underlying, and then we do exactly the same thing. So we go down, and now we have the 2 nodes, 2 input nodes. That's again partially active, keep the state, continue with that until we reach the full activation. So all the nodes are active within this rule, and now we can just add the owner discount inside the network itself. That will maybe trigger another rule, and we can continue like that. So why was Elixir really good at doing that? First of all, great library. libgraph, absolutely fantastic, really well done. I've used it in different projects as well. And with that, it was really, really easy to do all kinds of things and to work with directed acyclic graphs in general. Directed acyclic graph, who doesn't know, is just a graph which is directed. So one edge is, the edge is as a direction. Shouldn't have loops, although I have to test this into the Retex implementation. Yeah, and it's a graph data structure. Another great thing that I found out while working with that was how to do forward chaining and how to use, to keep the state and iterate over the graph without changing, without mutating the state of the algorithm itself. And then I came up with came across this paper, Forward Chaining with State Monad. I will share it later. It's from this guy, Konrad Zanek. I don't know how to pronounce his name. And yeah, this allowed me to do things like just enum reduce, go to over the network, take every node and accumulate it. So that was the original inspiration for this kind of code that you see there. Protocols, again, that was great because I can actually implement a protocol for the activation of each node in the layer, knowing that it is a different struct for each point in the graph. So I can just implement the activation protocol, and that allows me to create different kind of activation depending on where I am. So if I'm in a 2-input node, I will check that the 2 parents are fully active, so I'm active and I pass the token down. If I'm just a type node, I will do some kind of pattern matching against my type, et cetera, et cetera. So that was actually great. Another thing is that I could implement the active function for each node, where we can check even the negation of some nodes for more advanced and who knows already rated. So there, it was fairly easy to just implement different type of checks for the activation of each node before passing down the token. And that's what we actually saw it, and that's what I was showing before. So this is a node activation. It's actually the same node, it's just a different close of the function. And here we are just checking, actually there's something a bit crazy and fun in a fantasy world, but we are basically checking that the working memory element, the identifier of it is a variable, and that variable will be assigned to something that is already in the node. So we can allow even users to put wildcards into their own knowledge and data. Another great thing was recursion, as we already saw, because this made it really easy to do just an enum reduce, go over the network and just connect the nodes 2 by 2 until it doesn't match anymore, and then leave with the last node there and connect it to the production. So actually it was really fast. One last thing is that I've just published today a library called Neural Bridge, which puts together both the Sanskrit DSL and the Retex into an engine, a rule engine, so you can check it out and you can try it yourself. And what you can see here, I hope it's not too small. What you can see here is a full expert system in Elixir in action. So here you create the engine, which is just like engine new something. Then you pass down the engine, you compile the rules in this way, so you can have your favorite veterinarian doing that, and they will just be able to write their own knowledge in this DSL and with the given and then, and that will be compiled. And at the end, you would ask question to the user or do whatever you want, and then you could actually just input this data, which is working memory element that we just saw. And at the end, or all the time, or whenever you need, depending on your use case, you can check the agenda, see what needs to be done, and you can do it. And the cool thing about it is being completely like done in Elixir natively, you can just have anything actually in the agenda. So you can even take the bindings, make an API call, you can write something to the console, you can, again, do an interactive shell, like where the user has to answer those questions. So we go back to COBOL, Prolog, and you can do all sort of things that you want. It's a very early stage. I wouldn't recommend it right now to use in the production, but I will welcome anybody that wants to join and help out or see if that works for your project. And yeah, have a look at it, and feel free to talk to me if you have any question about it. And yeah, another thing is that the limitation of this whole system and this whole project is that I wouldn't use this as a query engine, for instance. So problems such as, let's see if we have more than one attribute of that kind, etc., as a count or as a select, I wouldn't do it here, but I would use an external system and another database where you actually store data. And I would rather use this algorithm and this type of way of coding just for checking that a specific pattern exists in our data. So for fraud system, for instance, we, instead of checking whether or not a relationship exists between two users, I will actually just return from the rated the fact that three entities exist, A, B, and the relationship between them, and then check in another database whether this is the case or not. So some sort of weak activation of it. So that's pretty much it. I hope I didn't go too fast. I know it was a lot. I'm not a super expert of graph DBs or data structures, so but I try to do my best, and yeah, I just wanted to share my journey.
Thanks, Lorenzo. I don't think it wasn't personally too fast for me. I really enjoyed it, but then again, maybe I'm a little biased because I like good old-fashioned AI. Everybody else, maybe you can help me sort of give Lorenzo a virtual round of applause somehow. Did that reaction work? I don't know.
Thank you.
Yeah. Okay. Great. So let's move on to questions. Unfortunately, I can't see any on the Q&A tab, but for those of us in the audience, please post them and I'll keep an eye on them. We have plenty of time to work through them. I have a question. So, I mean, you kind of already mentioned how it was difficult to implement some of this because I think a lot of the the papers out there with the explanations of the algorithm basically rely on mutation. I think that's what you were getting at. That's been my experience with some exhaustive searches that I've written as well. Yeah, and I was just wondering, what was that like? Was it difficult to move that sort of very imperative procedural knowledge or procedural algorithms into a functional paradigm?
So yeah, I was just very curious about the Rete algorithm, just because I've seen so much hype around neural networks and other type of AI. So what I wanted to do was try out like different things where you don't need too much data to start with, but you need just quality. And actually, when you basically found the rules, then you can do other stuff. And one of the things that I loved the most doing that was that it was actually a big challenge because, as you said, everything relies on mutation. So if you look at the Python implementation of it, or Ruby or JavaScript, everything is just mutating the nodes, adding something to them, adding their token, doing something, and then you do the same thing when you want to deactivate, for instance, a node. So it's like I try to do it in that way with Elixir by basically changing each vertex of the node all the time, but that was just not possible. It was a mess, and it's also not really good because then you may lose references and things. So at the end, I've been researching how to iterate over the graph without changing it, but still keeping track of everything that is active, that went there, that should be deactivated eventually, and all the rules have been activated. So what I come across was this paper for chaining with state monet. I tried to read it a lot. It was super tricky actually because it's very academic. But at the end, I was like, yeah, state monet seems to be really the way to go here, because what you want to do is you just want to reduce from the root, being this directed and acyclic. Go from the root and go down to every branch. I mean, you can optimize in a lot of ways. And then just make sure you can activate it, try to go down as much as possible, keep track of that basically in a map. And then at the end of the iteration, you just have a new map, which is the whole new state of the system. And the nice thing about that is that you can keep track of snapshot of each activation and each step actually of the graph. So you can say, okay, let's go back 3 times and remove this working memory element, like the last one. Let's say you want to do an edit. So the easy thing to do is that you just go back once and that's it. And then you have the previous state, I mean, given that you want to keep it there. And the other cool thing about it is that it's incredibly fast. Pattern matching in the name of the paper, I was like, has to be that. We can do it, something with it. Like pattern matching sounds familiar to me. And and it's incredibly fast. And actually there is an improvement that I'm making that is going to make like 500 times smaller. And so you basically can have bunch of knowledge of experts, like hundreds and hundreds of rules under 1 megabyte of memory, and computationally it's super, super, super lightweight. And I'm actually building a system for production. It's already there, but it's not published yet, where we took and absorbed all knowledge from veterinarians related to gastrointestinal issues of dogs and put them into the algorithm, which is basically also asking questions to the user. So even a question answer is a rule, and it's just, code in an Elixir app. So you can embed any type of code into the activation of a rule. It doesn't have to be a working memory element. It could be call this function that means asking the user to fill in this WME and then put it in the system. And that's how it works. And it's absolutely fantastic and really easy. And scalability, which is also an issue of Rete generally, it's also not a problem, because if you have thousands and thousands of rules, it's still very small. Like the worst case scenario I've seen, it was like 100,000 rules for 300 megabytes of memory, which was still, I mean, okay. And the normal cases, like from a couple of hundreds to 1,000, are still totally manageable, super, super lightweight. You can compile it on the go, and that's it.